Hello and welcome to our channel again. So here I am Suraj. So this is the next topic on the quantum mechanics as I have discussed about the normalizations, expectation value, quantum operators, about bit about the Schrodinger wave equations. So we have seen a very small and a very good concepts and the basic concepts in the quantum mechanics. So now we are going to do the real quantum mechanics. It means solving the Schrodinger wave equations for the different potentials is our main objective in this video, and our next upcoming videos we are going to discuss the solving of the Schrodinger wave equations through different potential, or you can say potential energy. So what's the potential energy or the potential energy? What does it really means? And is there any types of the significance in the quantum mechanics we are going to discuss about in this video? So now let's start our part 3 of the quantum mechanics, infinite square well, and a bit about the particular Schrodinger wave equations. So now let's start our video on this particular topic. So as far in my previous video lectures, I have written this first form of the Schrodinger wave equation. This is the partial second order partial differential equation. But now here you can see here that I have just changed this particular equation into this equation. So what does these two equations really means? So I have said that this particular first equation is the time dependent Schrodinger wave equation. Time dependent Schrodinger equation. So this is a time dependent Schrodinger wave equations, in which you can see here that this particular potential energy, so this is the potential energy, is dependent on the time. So this is a time dependent Schrodinger equation I have said in my previous video lectures. That's why we use this particular partial derivatives form, because in partial derivative we apply the partial derivative when there are more than one function. This means there are two functions, let's say, when we use the partial derivative. So if you want to know more about these particular partial derivatives, I will make a particular video explaining this particular derivatives, partial or a single derivative or different types of derivatives, and also a bit of the differential equations. But now in this video, but then let's say this particular derivative occurs when you just differentiate more than one functions. Why? Because you can see that here this particular wave function psi is both dependent upon the time and this position. That why I use this particular partial derivative form. But I have changed this particular equation into this particular equation. So this particular equation is what known as the independent time independent Schrodinger equation. It means the particular potential of the particle is not dependent upon the time. And this is the case because more generally, whenever we have to solve this Schrodinger wave equation, we use this particular time independent Schrodinger wave equation because it is very easy to use. We solve this particular independent Schrodinger equation and multiply it by the Wiggle factor. Whatever this is, I will discuss in the next video. So for ease, we just use this particular time independent Schrodinger equation form, which I will try to explain here that what are the changes in these two Schrodinger wave equation. So here you can see that everything is same. I have just changed this partial derivative form into a normal derivative, which is a single derivative which occurs when you just differentiate a function which is only one, which depends on only one function. When you differentiate, we uses this particular differentiation, but it is used when we differentiate the two different functions. So you can see here the difference, and the difference is in this particular psi. These both are not the same psi. This particular psi is both dependent upon the position and the time, but this psi is only dependent upon the position. So let me write it clearly that you will distinguish that psi x t is equals to this particular form of the wave function, which is a time dependent, into a non-time, or you can say that this particular position dependent and the time dependent. Here I have written clearly to distinguish between these two particular wave functions of the time dependent and time independent. So you can see that this particular wave function which exists in time dependent, I have just separate those values. First is the value which is dependent on the position. Second is the value which is dependent upon the time. So I just remove this particular time wiggle factor, then the particular Schrodinger equation forms becomes the time independent Schrodinger wave equations. But how generally we derive this particular equation, we see in the next video, that how to derive the time independent Schrodinger equation from the time dependent Schrodinger wave equation. In the next video you can clearly define this particular time independent Schrodinger equation from the time dependent. So for now you can imagine that I have just removed this particular time wiggle factor, and then I obtain this particular time independent Schrodinger wave equation. And to solve this, and while solving this Schrodinger equation, which form we will choose? So generally we will choose this particular form. This form we will choose to generally solve this form. We will choose to generally solve this Schrodinger wave equation. So now let's move into the part of solving the Schrodinger wave equation. So most important and the most fundamental concept while solving these particular Schrodinger wave equations is for different types of the potentials. But why potential? What potential exactly is? So you can understand this clearly in the atoms. That in atoms you can see that according to the Bohr's model of an atom, the electrons exist in an energy levels. So if electrons exist in an energy levels, it has certain type of the energies. So if you have to just remove the electron from one orbit to suppose that from ground to the excited state, you have to provide some extra energies. Why? Because the electron is bound to that state by the electrostatic potential energy. By the electrostatic potential energy, yeah, kinetic energy is also the factor, but to understand this, it also has the potential energy at that point. So to escape from that particular potential energy of that particular energy levels, we have to just apply extra energy by means of, we can say that, photons, so that it escape from that particular ground state to an excited states. That's why we study solving the potentials, because potentials arises everywhere in the atoms and in the different types of concepts, quantum tunneling, in the bound and scattering states, all that here the potential plays a role. That's why we say we are solving the Schrodinger wave equations for different potentials, because this arises in the quantum's world. Like in atoms it arises, so everywhere this particular thing arises. So the most common example of solving the particular Schrodinger wave equation is for the infinite square well. So what is this particular infinite square well, and what is connection with the potential? Now we will going to see this. So this is the first case of the infinite square well. So what is infinite square well? The infinite square well is a well which is infinite, and the potential energy at the wall of this particular well is infinite. It means at that particular wall potential energy is infinite, and also outer region of this particular well also the potential energy is infinite, and the inner area of this particular well is the area where only the particle exists, or you can say that this is the area inside the well where there is a potential energy is equals to 0 and the particle existed. Why particle? Because at infinity there is no chance of solving the Schrodinger wave equations. That's why the probability of finding the particle at outside the well is 0, and inside the well, yes, there is a probability of finding the particle. So now we're going to just solve this Schrodinger wave equation for this particular potential. Particular potential means inside the well the potential is 0, outside the well the potential is infinite, and also the at the walls the potential energy this, but at this particular walls we can also define the potential energy. So now we are going to just generally solve this Schrodinger wave equation. So let me here point out something, that this particular wells goes from generally from 0 to a, let's say from 0 to a. So now it will be easy to just solve this particular equation. So we are going to write here about the writing here these Schrodinger wave equation. So h cut square divided by the 2m, and here we will uses the time independent Schrodinger wave equation as I have said before, d square psi divided by the dx square plus the potential. Since the potential is 0, we will not going to write the potential. Why 0? Because inside the well the potential is 0 defined, and that's the case of the infinite square well, and this is equals to the energy and this wave function. So what we are going to do is that we are going to transfer all here this particular constants onto different side. So now we are going to do this. So the next step would be to just transfer this. So what we'll do is that d square psi divided by the dx square, d square psi divided by the dx square is equals to the negative of the 2 m e divided by the h cut square and into the side So we are just assuming this particular constant as k. It means whenever you study the wave packet concept, you may remember this particular formula, which is I am going to write here, that k particular formula, which is k is equals to the root under. So I'm gonna write here this particular equation so that you can just put down those value and solve the Schrodinger equation. So I have written this particular. So let's imagine this all particular minus 2me upon h cut square. So this k constant is defined as root under 2me divided by h cut square. So we can write this as the d square psi divided by the dx square is equals to the negative of this particular constant square and psi. So this is that case. Now we have to solve this differential equation. So we are not going to solve this particular differential equation because this might be very deep and this can take a lot of time. So I'm generally going to write this particular solution of this Schrodinger equation. This particular solution. So this particular solution of this particular Schrodinger wave equation is psi x is equals to the a sine kx plus b cos kx. So this is the solution of this particular Schrodinger wave equation. So if anyone you have studied deep differential equations along with the physics, you will point that this particular differential equation is a form of the harmonic oscillator. This particular differential equation is form of the harmonic oscillator, as this particle just collide to this potential, but here the potential is infinite so that it cannot escape, it just bounce back and it is going this particular fourth movement inside this well. So in some other videos we are going to just solve this particular differential equation, because this differential equation is also very interesting for the harmonic oscillator. So now let's focus on its solution, which solution psi x is equals to a sine kx plus b cos kx. So this is the particular solution of this Schrodinger wave equation. So there are some of the properties of the infinite square well that we are going to discuss here, but the properties are mostly very detailed manner, so it I think it will take another separate video of its explanation of its properties, that how we can find this particular a constant. I have to choose sine kx, cos kx. What is the most general form of this particular wave, this particular solution? Because this psi x is equals to a sine kx plus b cos kx is not the complete solution. There are some of the rules to define the wave function inside the infinite square well, which I am going to discuss in the next video. That what are the properties, how we can choose the wave functions in the infinite square well, because we cannot any choose an arbitrary wave functions. There are some of the rules that wave functions have to this or wave function has to follow, and if this particular wave function follows, then we will going to choose the wave functions. So there are some of the properties like orthonormality or whatever is it, which demands a separate video. So in the next video I'm going to discuss about the properties of the infinite square well. As in this video we have solved the infinite square well, and its solution is equals to the a sine kx plus b cos kx, but this is not the general solution. The general solution is the linear combination, whatever this is. This we have to go into deep of the infinite square well to understand this. So this demands another separate video. So in this video what we have discussed it about the difference between these particular equations, which is a time independent and the time dependent Schrodinger wave equations. And why we choose the time independent Schrodinger wave equations? Because it is very easy to solve firstly the time independent, and then we will multiply it by this particular wiggle factor to makes it the time dependent. That's why we generally solve first this and multiply it by this, and I will say that this only for the ease. Then we discuss about what potentials in the quantum mechanics is. Everywhere in the atom you can see that potential exists. In atoms, electrons are bound to the electrostatic potentials by the nucleus. It also has the kinetic energy. That's why you have to provide some of the extra energies, external energies to that particular electron to just exert or to just remove from this particular ground state to an excited state. So this is the thing which is part of the board. So I'm also going to start a lecture series on the modern physics, as a modern physics put lay down to this particular quantum mechanics, and I will go into the also the how the quantum mechanics develops, how the quantum mechanics develops, how the Pauli's exclusion principle and whatever any principle, how Bohr's prevents the collapsing of the nucleus, all that things. I will also going to start a separate series lecture for this. So you have to subscribe my channel so that you can get this amazing lectures on this particular type of the modern physics and quantum physics. So for now we have discussed about an infinite square well. In the next video we are going to discuss about the properties of the infinite square well. So I hope that you cleared out all your doubts regarding the infinite square well, or if you have any other doubts you can comment down the doubts in the comment, so that I have to know that what doubts you faced while watching this lecture. So thank you for watching my this video lecture on the infinite square well.